I'm Dhruti from Sri Venkateswara College of Engineering, CSEI Department, Bengaluru. Today, I will give a small presentation on representing knowledge in an uncertain domain. Let's move to the introduction. Introduction. Introduction to representing knowledge in an uncertain domain. Uncertain domains refer to areas where there is incomplete or ambiguous information. Advanced AI systems need to be able to handle uncertainty in order to make accurate decisions. Representing knowledge in uncertain domains is essential for AI systems to effectively operate in real world scenarios. So we can see that picture core areas of artificial intelligence. The first is the sensory AI IoT. Second, physical AI industrial automation. Third, cognitive AI worker training. Fourth, general AI easily adaptable. Fifth, precision AI learning from small data sets. Sixth one, explainable AI. Then, the challenges in representing knowledge in uncertain domains. Uncertainty arises due to limited data, conflicting information, or changing circumstances. Representing uncertainty requires capturing probabilistic relationships between variables, balancing the trade-off between accuracy and efficiency is a major challenge in uncertain domains. And we have some of the points for representing uncertain knowledge. Symbolic and numerical uncertainty, the closed world assumption, predicate completion, taxonomic hierarchies, abduction, truth maintenance, Bayes rule, certainty factors, fuzzy sets. Then we move to probabilistic models for representing uncertain knowledge. Bayesian networks. Bayesian networks are graphical models that are directed acyclic graphs to represent probabilistic relationships among a set of random variables. They are widely used for uncertain knowledge representation in various fields such as healthcare, finance, and natural language processing. These Bayesian networks allow modeling dependencies between variables and make probabilistic interfaces based on observed evidence. Then, Markov decision. Markov networks are undirected graphical models that represent probabilistic relationships among variables. They are used in situations where Bayesian networks might not be sufficient, especially for modeling complex interactions between variables with symmetric dependencies. Then the third, hidden Markov models. Hidden Markov models are the statistical models which are used to model sequences of observable variables whose underlying states are hidden or not directly observable. They are widely applied in speech recognition, bioinformatics, and natural language processing for modeling the sequential data with uncertain state transitions. Fuzzy logic for handling uncertainty. Fuzzy logic allows for the representation of imprecise or vague information. Fuzzy sets and membership functions are used to assign degrees of membership to elements. Fuzzy rules and fuzzy interface engines enable reasoning and decision making in certain domains. Fuzzy logic helps in handling imprecise data, that is, traditional logic relies on crisp binary values, they are true or false, whereas fuzzy logic allows for degrees of truth. This is particularly useful when dealing with data that's not clear cut and contains ambiguity or imprecision. Second, linguistic variables and fuzzy sets. Fuzzy logic uses linguistic variables and fuzzy sets to represent vague concepts linguistically. For instance, terms like hot, cold, fast, or slow can be represented in fuzzy logic to capture their inherent uncertainty and subjectivity. Third, membership functions. Fuzzy logic employs membership functions to assign degrees of membership. Instead of strict categorization, membership functions enable a gradual transition and not allowing for more the representation of uncertainty. Artificial intelligence approaches for uncertain knowledge representation. Probabilistic reasoning, fuzzy logic, ontologies with uncertainty, Bayesian networks in AI planning. So, the probabilistic graphical models such as Bayesian networks, Markov networks, hidden Markov models are extensively used to represent uncertain knowledge. They model relationships between variables, probabilistically allowing for reasoning under uncertainty. Fuzzy logic is employed to represent and reason with uncertain or imprecise information. Ontologies augmented with probabilistic extensions or fuzzy logic can handle uncertain knowledge representation. These ontologies allow for the explicit representation of uncertainty in relationships between entities in a domain. These Bayesian networks are integrated into AI planning systems to model and reason about uncertain states, actions, and outcomes. Evaluation and validation of uncertain knowledge representation. Metrics such as accuracy, precision, recall, and F1 score can be used to evaluate the performance of uncertain knowledge representations. Cross-validation techniques can assess the generalizability of the models. Real-world testing and user feedback are crucial for validating the effectiveness of uncertain knowledge representations. Autonomous driving systems. Then we move to the applications of uncertain knowledge representation in advanced AI. Autonomous driving systems rely on uncertain knowledge representations to navigate complex environments. Healthcare systems use uncertain knowledge representations to assist in diagnosis and treatment decisions. Financial prediction models leverage uncertain knowledge representation to make informed investment choices. Conclusion. So we learned representing knowledge in an uncertain domain is crucial for advanced AI systems to make accurate decisions. Probabilistic models, fuzzy logic, machine learning, and hybrid approaches are used to handle uncertainty effectively. Ongoing research and advancements will continue to improve the representation of uncertain knowledge in AI systems. Thank you.